optomechanical instruments. So here is you are trying to control this slit, and very precisely you want to do that. At the same time, you only want a movement in one direction, right? And they should move in. So I think this is the input motion. So you adjust at this point, and you should be able to get very symmetric motion. So of course the heart of it is this mechanism design. So conceiving this design and then connecting this parallelogram mechanism so that you can have. So if you move this, they move this one and this one apart by the same amount. Of course, what you see here is it's not symmetric design. So what will happen after some time? They move with a different magnitude, and you will not get the same benefit. So there is a limitation. So adjustable in width 0 to 1 mm, symmetrical with the bisector. But beyond that, it may not work. So further, so this is the embodiment. This is the basic design, and then you convert it into whole flexure design. And this is the input, and again, this is the input now. So you adjust this screw, and then you can move this one. So this green part is this member. You can see. So you move, and and you have a small spring here, so that is a preloaded because you want movement in both directions. So it's preloaded in one direction, and then by just adjusting it, you can adjust the opening here. So very nice mechanism. Similarly, suppose if you want a very fine and want a symmetric design, then they come up with this design. And again here, this is the input. So input is this member here. You move, and then it's translated from this member. And here what you see, if this parallelogram mechanism or a straight guidance mechanism is passing through the middle section, right? So this is what we learned. It should through the middle of the straight guidance mechanism if you want purely a straight guidance motion, right? Then you can control the motion here. So again, very nicely designed, and these are the things you can always like make a card, and you can get a 3D model printed. We can get a 3D can get it 3D printed. We can also check it. So anybody interested, you can just make a CAD drawing of this and pass it to me, and we can discuss, and I can get it fabricated. Okay. Yes, we'll continue. Just give me a little break. So if you got hold of the book, I think all these examples are from the book, and just go through because very nicely designed and useful. In this case, also in this example, you want to adjust the orientation of this mirror. So this is the mirror you're talking about. So you have adjusted it, but suppose if it's for some optomechanical application, or suppose if it's mirror of coming or a design for some space application, this phi is very important, adjusting it. So it's not just about the assembly, but after assembly, whether you can fine tune it, whether you can manipulate it. And in many of the these precision machines, what you realize that assembly is one aspect. So assembly one should do, but at the same time, after the assembly, you should be able to do the finer adjustment, and that's the essence of I would say of this course. In this case also, what you see, they are very selectively, you have hinges here. So identify those hinges, and many times in the exam I'll ask also, okay, can you identify the flexure members and whether it's possible to make the equivalent rigid link mechanism. So here you can see this, right, how it works. And this is the equivalent mechanism, right? And what's happening here? If you have a screw 1 and a screw 2, the screw 2 is for coarse adjustment, right? And the screw 1 is for fine adjustment. How? So when you adjust this screw 2, right? Why is saying coarse is because if you adjust this, you are pushing this member with respect to the base. Suppose this is the base, right? So what will happen if it gets pushed, this point to move, right? And this entire thing will hit, right? Entire thing. But suppose if you want a finer adjustment, then you will start adjusting this screw 2, screw 1. So what will happen in this case? When you start adjusting, you push this member, right? And when you push this member, basically what you are trying to do is you try to move this member outwards, right? So it will rotate because this link from this point to this point, there is a link, right? Equivalent link. And when you push, actually you try to rotate, and as it get pushed, right? This point will, so there is another link here. So as it moves away, moves in this direction, this will move in this direction, right? So equivalently there will be movement here, and because of that, so mirror is actually attached to this link. There is another hinge here, and this will rotate. So just by moving this up and down, so this is one extreme. Either way, it will move towards this direction, and with that you can adjust this phi very accurately. So this is for angle adjustment for the mirror. One of the other application of this elastic members or the flexure is also elastic adjustment. And what you realize here is, if you take a cantilever, so this is the cantilever member, and suppose so it's a clamp here, and if you adjust u in, and suppose you attach a member at this point at let x, so this is output, u out, right? So u in and u out. So if it's a rigid member, what will happen? And suppose if so, you get a linear relationship x by l, right? By that. But if it's an elastic deformation, and if you make use of this, actually you get q, x by l to the power q. So 3 times, so many times. So using this method, you can adjust to a very fine level. And one of the application is in suppose if you are guiding some very thin materials, and they have to be guided using these rollers. You want that this axis, this bearing axis, they should be aligned perfectly, right? But with assembly you cannot do. So after the assembly you need to adjust. So here what you see, like side L, you say L and R, they are in different axes, what you can see. So if you adjust from here, right, you move this bearing axis up and down, right? Here if you adjust along this axis, you move in this direction, and that's what is required. So suppose you have this roller, either you can adjust, means you fix this point and you adjust, there are 2 axes only. So here you decouple, One you are moving in vertical direction and one moving in horizontal direction. And by doing that, you can precisely align it with respect to the other rollers. And then you can guide it really well. You might have seen that when you like any kind of screen, roller screen you try to do, and if it's not adjusted properly, then it starts winding to one direction. And if it's very fine and you want to do it well, it has to be adjusted very accurately. So this is one of the application. Uh, I have some more examples. So talking about the torsional members, so torsional compliance. So these are the hinges, right? So using the whole flexures. But that kind of thing you can also get with the L cross section. So if you get a section here, is L. This is the section, right? So any kind of open section, and if you just apply this torsion, actually it can twist easily. So this is another example. Here is a cross member. Here also you apply, you can twist. So this is very one recently I got fabricated, and you can see it's just one piece, and using this member. So very nicely done, and it can be done. So don't think is, and I can get a very large motion, and it's just all one piece, 3D printed. So one of the thing what in this case, if it's L, actually it tries to bend, and for obvious reason, because if you start twisting, other fibers will try to one try to extend and one try to, because it's getting elongated, so it will try to pull. So there will be deviation, so it doesn't work. So this is a kind of design guidelines. L by A should be more than 6. So this L and this thickness A. So L by A must be greater than 6. Then only it will work. Otherwise, there will be, if it's a short, then you will have those deformations. This is just example I have shown with the cross. So this one you can do, and you can get rid of this bending, or you can even get this. So here, suppose if you have this member and you simply remove this section diagonally. Actually, this part is hardly of any use. So that's what. So you can make diagonal members also. Even if you take just a leaf spring, it will also give you that torsional behavior. But yes, as you start twisting, it will get a stiffer and a stiffer. So there are some more examples. Suppose if you want to design this universal joint. So universal joint means this alpha and beta rotation, 2 rotations you want, right? So okay, it's a member again. Here you have the leaf spring and using wire flexure. So this leaf spring and wire flexures, by combining this way, you should be able to get the rotation. So I would like you to try and see yourself whether you can get these motions, because we have discussed a lot about controlling degrees of freedom, and one should be able to either design or explain how these alpha and beta motions are possible in this case. Okay, so the equivalent is, this is leaf spring, so equivalent is 3 wire flexure, right? One should be able to know. And then you have 1, and then just explain. Okay, if you have a member connected, so wire flexure, then you have wire flexures here, and then okay, and from this also you have one, and then another one. Suppose if you have one should be able to explain, right? So I expect that you should be able to explain how you are getting these motions alpha and beta in this case. Of course, you can also get an elastic ball joint equivalent to a spherical joint by using 3-wire flexures. But what you have to be aware is they don't have a common code because of physical limitations, right? But still, it can give you a similar behavior, and if it's sufficient, then you can use it. So, very good application is for adjustment, orientation adjustment of an antenna. So any antenna you want to adjust just to. So you don't want this rotation. So this is not required. This adjustment is not required. But of course you want this adjustment and this adjustment. This is not right because the disk you want to just either do this right or up and down. So it's called meridional theta and azimuthal direction, right? So how to get that? And you can see that you can use servo motors. There are 2 servo motors here. So this member. So these are linear actuators, and then you need the spherical joint here. So a spherical joint you get here, right? And these are just a structure. So this a structure using trusses, but then very selectively you can get. So this is the basic mechanism. So you have a spherical joint, you have another spherical joint, and how these 2 actuators, when you move, you can control these 2 directions. So again, very good example, and so this is also from the book. And if it's not clear, maybe in next lecture, let me know, then we can discuss it further. So you can see that just by adjusting it, it can rotate along these points. And similarly, when you adjust one, you can move, so it can rotate, right? And here it can rotate along this direction. So these are the embodiments. So I think let's stop here. There will continue, and there are very nice example. You can make a very useful flexure using even tubes. So even these plastic tubes, you can cut and make a slit, make holes and slit it, and then you can get cardon coupling is basically universal joints, and then you can get very different kind of flexures with different degrees of freedom, and they are used for even like making piezo stacks, and so we'll discuss in the next class, and we'll talk about the negative stiffness also, how you can work in a region where it's almost like 0 stiffness and you push it, and wherever you leave it, it can stay there. So some examples, and we'll talk about it.